This is Lab 4, Circuits and Capacitors. One of the main goals of this lab was to explore how various aspects of circuits affect the charging and discharging of capacitors. Some of the major physics principles in this lab are circuits, capacitors and resistors, and Kirchhoff's loop rule. By following the procedures in this lab, I was able to create various circuits to observe the changes in voltage and current. Additionally, I was able to create an accurate time-dependent model of voltage across a discharging capacitor with a slope coefficient only 3.4% different from the theoretical value. So we began this lab by creating a series circuit consisting of two 1.5 volt batteries, two resistors of 47 ohms and 100 ohms respectively, and some ammeters that showed the charge across the entire circuit, which matched up with what we theoretically calculated with the EMF of the battery equal to the I of the circuit times the resistance of the circuit. We then used a voltmeter to observe the potential difference across the circuit to confirm the loop rule. So as we go across batteries, we should see an increase of their voltage of 1.5 volts. And then as we go through resistance-less wires and ammeters, we should see a flat line. But as we go through a resistor, we lose some of that voltage, so we see decreases between each of the resistors, which gets us back down to zero, which confirms the loop rule. Next, we created an RC circuit consisting of a 9-volt battery, a light bulb of varying resistance, and a 200 millifarad capacitor. In this circuit, we were able to observe and measure the time it takes to charge and discharge a capacitor with varying resistance. We observed that the light bulb initially was very bright, and then as over time, it slowly got dimmer and dimmer. It took roughly 20 seconds for a 10 ohm light bulb for a capacitor to charge and discharge. And we saw that for a 20 ohm light bulb, this value was doubled to about 40 seconds. We were also able to observe that as we charge and discharge the capacitor, the current must be decreasing as the light bulb got dimmer and dimmer. Additionally, while this appears to be a lot of time, a majority of this time was spent with the light bulb appearing to be basically out while there was still some charge approaching the 9 volts or the 0 volts. Finally, using a similar setup to the previous circuit, we were able to observe the time dependence of the voltage across a discharging capacitor. In this setup, we used a light bulb with a resistance of 30 ohms instead of 20 or 10 ohms, and we used the stopwatch to record the voltage for the first 20 seconds. As you can see here, in the first second, the light bulb is burning very brightly, and then after about 10 seconds, it's still very, very dim, but it still has some charge on it. And after 20 seconds, it still appears to be out, but there's still a tiny amount of charge left. Since the voltage in the capacitor decreases rapidly at first, then much slower as time goes by, it follows an exponential equation. This is modeled by delta V is equal to delta V naught times e to the negative t time divided by resistance times the capacitance. So to create a linear model of the time dependence, we take the natural log of the equation, which yields natural log of delta V is equal to natural log of delta V naught minus t divided by RC. So we take our data for the first 20 seconds of discharging a capacitor, and we can see that over time it decreases very slowly after the first initial sharp decrease. And we know that the initial value should be 9. So we take the natural log of these two divided by each other, and we get a nice linear model of the discharging of the capacitor according to time. So this 0.1609 is our observed value for the slope coefficient 1 divided by RC. So to compare this with the theoretical value, we have 1 divided by the resistance and capacitance of our circuit, which was 30 ohms times 0.2 farads, which is equal to roughly 0.1666 repeating, or 1/6. This is only a 3.4% difference between the values, indicating a good model of the time dependence of the voltage across the discharging capacitor. Now, what if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? An ideal ammeter has zero resistance to avoid losing any voltage. However, a real-life ammeter would create a high resistance in a circuit and therefore cause the current reading to be lower than the actual value if an ideal ammeter was used. Now, what if we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in this circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Well, if there was no resistor in a circuit with a battery and a capacitor, then ideally the capacitor would reach a full charge almost instantaneously. However, in real life, it would not be instantaneous because there would be some resistance within the battery and capacitor. And additionally, such a rapid movement of energy could cause some kind of explosion and rendering the experiment useless. By following procedures set in this lab, I explored the various aspects of circuits and their effects on the current and voltage. I was also able to create an accurate model of the time dependence of the voltage in a discharging capacitor that was only 3.4% different from the theoretical value. Thank you.